So here's an example where I have my same point, 5 comma 4.5, but now I've chosen a basis that isn't even rectangular anymore. But the principle is still the same. If I want to know what are the coordinates of this point 5 comma 4.5 with respect to this basis, and here this basis is 2, 1, and negative 2, 3, then let's do it first of all graphically, starting from the origin, and first going along my first basis vector direction. I'm going to count 1, 2, 3 multiples of that first basis vector. See how I'm going this time? Diagonally instead of horizontally, because that's the way that my first basis vector points. So I'll go 3 in that direction. And then I have to count upwards. And upwards here means in the direction of the second basis vector, so that direction. I'm going to count upwards what looks like about 1/2 or so. And so we can make a prediction that the coordinates of this point, 5 comma 4.5, with respect to our new basis, which isn't even rectangular anymore, our prediction might be that those coordinates are 3 comma 1/2. We could verify that prediction by finding this linear combination. In other words, to use the notation of the book, what we would be doing here is we would be saying that the vector whose coordinates are 3 comma 1/2 with respect to this basis is by definition equal to that linear combination of those two basis vectors, so 3 times the first one plus 1/2 times the second one. And if we work all that out, 3 times the first one is going to be 6 comma 3. That would be this point right here. And then 1/2 times negative 2, 3, that's going to be negative 1 comma 1.5. That would actually be this point right there. And when I add those 2 points together, wonder of wonders, we get 5 comma 4.5. So these are indeed the coordinates that we were looking for. But if we wanted to be absolutely certain, we probably should have set up the vector equation, which turns into a matrix equation that would solve this system. Let's just do that really quickly as well. That the vector equation, which looks like x, or c1, let's call it, times 2, 1, plus c2 times negative 2, 3 is equal to 5 comma 4.5. That vector equation would have as its first column the first basis vector, 2, 1. Its second column would be the second basis vector, negative 2, 3. And the right-hand side would be 5 comma 4.5. And so to discover those coordinates, we would just have to solve this augmented system. Well, apply the row operations that you like. We're just going to, let's whiz over that real quick, because I'd rather not dwell on row operations today. But when we finish this solution process, we should get that as our coordinates out. So our first coordinate is 3, our second coordinate is 1/2. But now the point I wish to make is that this process by which we take the standard coordinates of a point and convert them into the non-standard coordinates of a point, so the process that takes us from 5 comma 4.5, which are the standard coordinates, into non-standard coordinates like 3 comma 1/2. But that process is always the same. Namely, for a given basis, we're always solving the same system of equations. In other words, the matrix on the left-hand side is the same. The only difference is what's on the right-hand side. So all the steps of row reduction are the same for a given basis, which means that we should be able to solve a whole bunch of these systems of equations all at the same time. And what I mean by that is, to find the b coordinates of a point, if I know the standard basis coordinates of that point, should always be the same system of equations to solve, which means it's always the same matrix, which means I should be able to use the inverse of that matrix to get my b coordinates. So if my b coordinates are right here, and I happen to know what the standard coordinates I'm looking for are, x, y, then the matrix, which turns b coordinates into standard coordinates, is the matrix whose columns are exactly the vectors in my basis, v1, v2, times whatever my coordinate vector with respect to the basis is going to give me the standard basis vector. So in other words, the matrix A, whose columns are my basis vectors, the job of that matrix is to turn b coordinates, those, into standard coordinates. Namely, those. So in other words, if I were to put together, in this example, the matrix 2, 1 as the first column, negative 2, 3 as the second column, then I would find out that if I multiplied that matrix by the b coordinates of this point, 3, 1 half, that I would get the standard coordinates of this point, 5, 4.5. But that's not usually the way that we want to go. Usually we want to go the other direction. I know the standard coordinates of something, and I want to find the b coordinates of that something. So in other words, if I want to reverse this process, what matrix do I need to do it? If A turns b coordinates into standard coordinates, then what matrix is going to turn standard coordinates into b coordinates? The inverse. We just need to do the opposite of whatever A does. So let's just use our 2 by 2 shortcut and find out what is the inverse of this matrix 2, 1, negative 2, 3 in the columns. How does the shortcut for 2 by 2s work again? So there's the inverse of our matrix. And the claim is that this inverse should turn standard coordinates into matrix coordinates. So let's try picking a different standard coordinate and see if we can get the b coordinates out of it. So let's say I pick a new point, maybe, I don't know, how about this point right here, which looks on this to be 6, negative 5. So the standard coordinates of this point are 6, negative 5. Let's try to use this inverse matrix to discover the b coordinates of this point. I'll just multiply this matrix by that vector. 3 times 6 is 18, minus 2 times 5 is minus 10, so 18 minus 10. Oh, I got a 1/8 out front here.
Where did 6, negative 5 come from?
Oh, I'm just picking another point here.
Oh.
So I'm picking on this point right there, and I'm going to try to find out what are its b coordinates. So if I choose the point 6 minus 5 and then multiply by this inverse, then the first entry is going to be 8, which I'm going to multiply by that 1/8 at the end. My second entry is negative 6 minus 10, so that's minus 16. And then 1/8 times that vector is going to give me 1, negative 2. And so, over here on the side, let's organize what we just attempted to prove here, is that we're claiming that the point whose standard coordinates are 6, negative 5 has as b coordinates 1, negative 2. Well, how do we know if that's true? Let's verify by just counting graph paper squares, which aren't squares again. They're parallelograms this time. But if I count them out, again, my standard coordinates of my point, 6, negative 5, that was right here in our picture. And the coordinates with respect to the basis b, we think are 1, negative 2. How come? Because starting at the origin and going 1 square in the v1 direction, and then 2 squares in the opposite of the v2 direction. Sure enough, it gets me to that point. So that gives us kind of the recipe for how to translate between standard coordinates and non-standard coordinates. Is if I know the standard coordinates of a point, and I'd like to know the b-coordinates, the non-standard coordinates of a point, then the matrix which achieves that change of basis is the inverse of the matrix that has our basis vectors as its columns, v1, v2. And if we're in 3 dimensions, it would have v3. If we're in 4 dimensions, it would also have a v4, and so on. So all we have to do is make a matrix whose columns are our basis, find its inverse, and that inverse has the power to translate standard coordinates into b coordinates.